In this lecture, I will solve two problems based on unbiased series clippers. In case of unbiased series clippers, there is no biasing present in the clipper circuit. This means there is no additional DC voltage source present in the clipper circuit. This is the example of unbiased series clippers because there is no biasing, there is no additional voltage source present in the circuit, and diode is in series with the load resistance. There is only one voltage source, and that is Vi, the input voltage source present in this circuit. In the first problem, we need to determine Vo, the output voltage for the input shown. This is the input waveform, and we have to find out output waveform depending on this input waveform. For the first half cycle from 0 to T/2, Vi is equal to 20 volts. You can see it is equal to 20 volts throughout the first half cycle, and this will be the polarity plus minus. Current will flow in clockwise direction from positive to negative, and the direction of arrow in the diode symbol is similar to the direction of current. So the diode is forward biased, and I will replace it with short circuit because it is ideal diode. If there is actual diode, then we have to replace it with the barrier potential VB, but we have ideal diode, so we can easily replace it with the short circuit. And now I will find out Vo using the Kirchhoff's voltage law, and it is equal to Vi. Very simple. In the next step, we have to find out the output voltage Vo for the next half cycle from T/2 to T. This is when the time is from 0 to T/2. And before moving to the next half cycle, I will first plot the output waveform for the first half cycle, and I have already explained you in the last lecture that it is good to plot the output waveform just below the input waveform because this will reduce the chances of error. I will extend these lines to have the same scale. This plot is for the output voltage Vo, and for the first half cycle from 0 to T/2, it is equal to Vi, and Vi is equal to 20 volts. So the output voltage is simply equal to 20 volts. This is 20 volts. Now we will find out the output voltage for the next half cycle, and for the next half cycle Vi is equal to minus 5 volts. Vi is minus 5 volts. This means polarity is reversed, minus plus, and the diode is reverse biased. So we have open circuit in place of this diode. There will be no current in this circuit, so output voltage Vo is equal to 0. Very simple. And this is for the next half cycle from T/2 to capital T, where T is the time period. So the output voltage is equal to 0 for the next half cycle. It is equal to 0. And again we will have output voltage equal to 20 volts for the next positive half cycle, and this is the answer for the first problem. I hope this is clear to you. In the next problem, we will again try to find out the output voltage Vo for this clipper circuit, and we will also plot the output waveform just below the input waveform. For the first half cycle from 0 to T/2, Vi is positive, and we have this polarity plus minus. This will be the direction of current, and it is not similar to the direction of arrow in the diode symbol. So the silicon diode is reverse biased, and we will replace it with the open circuit. And because of this, there will be no current through the load resistance, and output voltage Vo is simply equal to 0 volts. I will first plot the output waveform for the first half cycle, then we will find out the output waveform for the next half cycle. I will again do the same thing. I will again plot the output waveform below the input waveform Vo. Output voltage is equal to 0 for the first half cycle from 0 to T/2. Now we will find out the output voltage for the next half cycle from T/2 to T. This will be the polarity minus plus. Direction of current is from right to left, and it is similar to the direction of arrow. So the silicon diode is forward biased, and we will replace it with the barrier potential because this is practical diode, not an ideal diode like the previous case. 0.7 volt is the value of barrier potential for silicon diode, and we will find out the output voltage by using the Kirchhoff's voltage law. We will apply the Kirchhoff's voltage law for this negative half cycle. There are two ways to do this. Let's say this is the first way and this is the second way. In the first way, we are considering Vi, and in the second way we are considering minus of Vi, because the polarity is minus plus. So we are considering minus of Vi for this case and we are considering plus of Vi for this case. I will quickly find out the output voltage for this case. The direction of current will be clockwise from plus to minus. So we have plus of Vi plus of 0.7 volts plus of 0.7 volts, then we have minus of VO equal to 0. This implies the output voltage is equal to Vi plus 0.7 volts. Now we will find out the output voltage for the second case. The direction of current will now change. It will be anti-clockwise. So we have plus of Vi, we have plus of Vi, plus of VO, plus of VO, and minus of 0.7 volts. Minus of 0.7 volts equal to 0. This implies the output voltage is equal to minus of Vi plus of 0.7 volts. We can use both these equations to obtain the output voltage, but we have to be careful. Let's take one example to find out what is the difference between the two equations. Let's say at this time, at time Tm, we want to calculate the output voltage. Input voltage is equal to minus 20 volts. So VO is equal to minus 20 volts plus 0.7 volts. It is equal to minus 19.3 volts. Now we are interested in calculating the output voltage using this equation. At Tm, the input voltage is equal to minus 20 volts, but for this equation we have already considered minus of input voltage. So we have to just consider this 20 volts. We do not include the minus with this 20 volts, because if you do this you will have minus of 20 volts, which is wrong because we have already considered the input voltage to be negative. So we will just consider 20 volts plus 0.7 volts. When you solve this you will have the same result, minus 19.3 volts. So you can use any of these equations to obtain the output voltage, but you have to be careful regarding the sign of the input voltage. But there is one constraint in using this equation. These two equations are valid only when the input voltage is greater than the barrier potential of this silicon diode, because when input voltage is smaller than the barrier potential, that is 0.7 volts, the diode will remain off and there will be no current through the load resistance and output voltage will be equal to 0. So we have to show the barrier potential, that is 0.7 volts, and because of the position of the diode we have to give minus 0.7 volts to make it forward bias. This is the point of intersection between the 0.7 volts line and the input waveform. I will extend this point like this, and I will also extend this point of intersection like this. Now you can see for this portion of the waveform and for this portion of the waveform, the input voltage Vi is smaller than 0.7 volts. So the output will be 0 because input voltage is less than the barrier potential. So it will remain 0 for this interval of time and it will remain 0 for this interval of time. After this, the input voltage is greater than the barrier potential, 0.7 volts. So we have the identical waveform, we have the identical sinusoidal waveform, because we are just adding 0.7 volts to Vi. Vi is sinusoidal, and when we add 0.7 volts to Vi, there is decrement in the magnitude by this value, by 0.7 volts. The maximum or peak value is equal to minus 19.3 volts, minus 19.3 volts that we have already calculated by using the two equations. So this is how you have to plot the output waveform in which there is actual diode. You can use the two equations, but you have to be careful regarding the sign of the input voltage, and you also have to take care of the barrier potential. If the input voltage is smaller than the barrier potential, diode will remain off and there will be no current through the load resistance and output voltage will remain zero. There is one more thing that we have to find out, whether this clipper is positive clipper or negative clipper. You can see we have clipped the positive portion of the waveform. We have clipped the positive portion of the waveform. So this clipper is positive clipper. This clipper is positive clipper. And in problem number one, we clipped the negative portion of the waveform. So this clipper here is negative clipper. This clipper is negative clipper. This is all for this lecture. I hope everything explained in this lecture is clear to you. In the next lecture, we will solve few more examples related to series clippers.